Das here from LG Institute of Engineering and Technology. In the previous session, we have discussed lots of stuff regarding superconductivity that includes its property as well as the basic concept for the same, that was a BCS theory. In this session, we will describe about the London theory, or you can also say that London penetration depth. Now, let's check out some history about it. So it was actually proposed in 1935 and it was proposed by the two physicists, well-known physicists, Fritz and Hens, London. They were together also known as the London brothers. Now, basically, what was the scenario and what is the significance of it? The significance of the London penetration depth or London theory is that it describes the Misner effect and the zero resistivity. But along with the Misner effect, they also described something new that we will discuss later on. And how they did it? They did it with the help of the Maxwell's electromagnetic equation. So they utilized Maxwell's fourth as well as the third equation for proving their theory. Okay. So now, before we start the theory, let's have some brief glance of the thing, that is what is Misner effect. So basically we have studied this in the property, and the Misner effect says that the complete expulsion of all magnetic field lines from the superconductor is called as a Misner effect. It also justifies the diamagnetic property of the superconductor. How it was actually happening? You can say that, for example, that is the superconductivity, and in that we are saying that magnetic flux line or magnetic field density is almost zero. So how it is happening? So what happens when we are taking a superconductor? We are assuming that it is a round now. So circle, in that you can see that the magnetic flux line or external flux line is just getting away from it. It is not allowed to penetrate to it. Okay. So this was all about Misner effect. Now, when you studied the Misner effect, now this was an ideal condition, but the concept of the London theory was a practical approach. And what they saw in practically, they saw that the Misner effect doesn't occur abruptly at the surface, or you can say that that expulsion was not happening at the surface. Yes, expulsion was there, but not at the surface. Rather than what London theory predicted, that the magnetic field lines penetrate and exponentially decreases. Now that is a non-ideal condition, or you can also say is a practical condition. Okay. So what was the Misner effect? Misner effect was justifying that the magnetic flux line will be expelled from the superconductor. Okay. But rather, what did the London brothers actually predicted, or they saw that it was actually penetrating at some extent, and slowly and gradually it was increasing. Okay. So now what was happening? For example, we consider that the same circle of the superconductor. Okay. And then we apply the magnetic field line of BA. So we are naming it as a BA, and you can see that it is exponentially decreasing. So when it is exponentially decreasing, so what is happening? We are just getting the coordinates, and we can say that the point at which it is happening, that is the penetration depth. Okay, and where the exponentially decreased, okay, magnetic flux line is happening, that point is penetration depth, and x is the length at which it is increasing, or how deep it has been penetrated. Now the point that has been actually pointed out here, that is the blue point or blue circle, that indicates that at particular that point what is happening, that is the B, that is the magnetic field strength at that particular point is equal to 1 upon E, that's of the applied magnetic field. Okay, so this is happening at that particular point. So from this we can say that the B inside is nothing but the magnetic field generated or magnetic field within the superconductor is equal to BA, that is applied magnetic field, into exponential of, that is E or raised to minus x upon lambda L. Then minus x is the distance. Okay, actually we don't want that it should penetrate. That's why we are taking the reference 0, and from that the length it is penetrating is minus x. So this what we have got, and that after that, okay, so after that now we can define that exponential decay of magnetic field line at the interior surface of a superconductor is called as a London penetration depth. So it is all about how much deep the magnetic flux line is penetrating and how it is decaying slowly and gradually. So this was defined by the London penetration depth definition. Okay. So now before we start of the theory, let us have some overview of the Maxwell equation that will be utilized here. So the Maxwell equation, in Maxwell equation, the first one is curl into electric field equals to minus B, that is nothing but the rate of the change of the magnetic field lines. Okay. So in this context, what it means to say when you say curl, curl is nothing but it is the change or it is the effect of any field when it is seen over a material. So what change in material is there in respect to property or any other extent with respect to the field given to it? That is what is defined the curl. So you can say that the Faraday's law says that curl of E, that is the electric line, equals to minus of rate of change of the flux line. Okay, so if you take an imaginary circle and penetrate the magnetic flux line through it and it is changing, so what happens? The outer surface, what is happening? The electric field is generated or electric field line is generated, but that will be exactly opposite of the magnetic field. Okay, this is why it is minus dB upon dt. That is the rate of change of the magnetic flux line. Okay, now this was the Maxwell's third equation. After that, we have got the second equation, and it is an interesting one. Second equation is curl of B equals to J plus rate of change of electric field. Now you can say that in the previous it was the curl of E, that was the change in the electric field. Now here is the change in the magnetic field, so it is correlated somewhere. Okay, so along with that, it says that curl of B, or you can say that the change of B is equal to J. Now J stands for the current density plus rate of change of electric field. So we'll go by one as we have got the two terms. So the first term we will take J. Okay, so when we are taking J, an electric field is generated. Okay, so you're from conductor, what is happening? The current is flowing, and surrounding it, you can see that magnetic field line would be generated. So with the rate of the change of the current density flowing through the conductor, your magnetic field will change. That is the curl into B equals to J. Now, when you take on the second context, we will take the second term, that rate in the change of the flux line or rate of change of the electric field flux line. Okay, so when we are taking that thing into the consideration, we are imagining that in that conductor now we are taking the two parallel plates. So when we are taking this two parallel plate, what will happen? The current that will be flowing, that will be now alternating in nature. As it is alternate, so magnetic field line would be also in alternate of nature. Okay, and it will be changing with respect to that whatever the current is flowing. So as AC would be there, so alternate magnetic field would be also there, and that happens throughout this plate. So this was the Maxwell's two equation that would be utilizing in our derivation for the same. So now we can start with the London calibration. That when we say that London equations, so first equation we need to get that suppose the magnetic field is applied to the superconductor, which is the function of time. Okay, so we are providing a magnetic field to the superconductor, seeing that it will vary with respect to the time, means it is a time v. After that, this varying magnetic field gives rise to the electric field according to the Maxwell equation that we have already seen. That equation is curl into E equals to minus 1 upon C dB by dt. That is nothing but the minus of the rate of change of the magnetic flux line. That what we have actually studied, or you can also do the rate of change in magnetic field that is changed with respect to electric field E. Okay, so now when we start with the equation 1, so we are assuming that when your super carriers are flowing. Now what is that super carrier? So when through conductor, or you can say that now it is a superconductor. Okay, so in superconductor, when your carriers are flowing, now we know that the carriers are in the terms of Cooper pen. So when this are flowing in that, and when the electric field is induced, so what will be happening? We know that the electron flow is always in the opposite of the electric field applied, right? So we are assuming that it would be having the mass of m. Okay, so when we note that, so what would be happening? The electric field is applied and the carrier would be moving just opposite direction, right? So we can define as force acting on that carrier now equals to mass into acceleration. Now acceleration, instead we are writing dvs upon dt, where vs is nothing but the velocity of the superconductor carriers. Okay, that can be also written as force equals to minus E into electric field applied. Now minus E is nothing but the charge. Okay, so this would be our first equation. Now after that, the field induced. After that, the field induced supercurrent density can be defined in the obviously in the term of J. So Js, now again we are using the suffix S, that is standing for superconductor, equals to minus E ns Vs. We know that it is the velocity of the carriers and ns is the number of the actually the number of the carriers. Okay, that is standing with ns. So from this first and second equation, okay, from the first and second equation, when we equate it, we will get djs upon dt equals to ns e square e upon m, and that's the London's first equation to be derived. Now after we are getting the first equation, now what will be getting? Taking curl on the both the sides. So after he took the curl on the both the side, what will be the scenario? M upon ns e square into bracket curl of djs by dt bracket close equals to curl of electric field. That would be our third equation. After that third equation, what would be the scenario? After that third equation, when we are going from the Maxwell equation, now we already know one equation, that is curl into electric field equals to minus 1 upon c dp by dt. This we have already recalled previously also. Okay, so now this equation is to be substituted in the equation number 3. So that substitution will give us nc upon ns e square into bracket curl into bracket djs upon dt plus db upon dt equals to 0. So what we did, we substitute the value and equated all the terms on one side with respect to 0. Okay, so that what we have done by substituting the value in equation number 3. After that, when we are taking the next one, so to obtain the Meissner effect, they removed the time derivative. So actually, London brothers were getting out the Meissner effect. They never wanted to prove the London penetration depth or something like that. That was just the observation of it. Okay. So meanwhile, when they were finding for the Meissner effect, what they did, they took out the time derivative. So when we are taking the time derivative, that is dt out. So final equation that we will get mc upon ns e square into bracket curl into js plus b equals to 0, and then they named it as a London second equation. So after we have got the London second equation, now the supercurrent density is related to also magnetic field by another Maxwell equation. That was obviously equation number 4 that we have derived. Okay, that was with respect to the current density. So that is Js equals to C by 4 pi into bracket curl into B. Okay, so now it is obvious, you can see that above Js is there. What would be the next step? Obviously, we will be replacing that thing. So the equation 5 will be replaced in the second equation, and that will give us, substituting the value, we will get mc upon ns e square into bracket curl into c upon 4 pi into bracket curl into b bracket close plus b equals to 0. Now what we are doing, we are taking all the constants out. Okay, so when we are taking all the constant out, that is mc square upon 4 pi ns into e square into bracket curl into b bracket close plus b equals to 0. This in this, the constant term were termed as a London penetration depth, and this is how we got the London penetration depth. So you can clearly see that London brothers were actually after the Meissner effect, how it was functioning. But meanwhile, practically they also got that it was penetrating at some extent. Okay, so why that is decaying actually? Because after certain point, when the supercurrent is flowing through the superconductor, its electric field would be generating a magnetic field, and that magnetic field actually repels the external field, which results into the decay of the external field. that what it was studied by the London brothers and that was concluded by them. So hope you guys have enjoyed the video, understood it. Stay tuned, we will see you in the next lecture.